So welcome back. We're carrying on with our study of functions, inverse functions, and logs. And yesterday we learned an exciting new trick whereby we can now solve for a variable in the exponent. So we're going to practice that a little bit more. And in fact, we're going to dive into two other topics that we've previously studied. One of them very recently. And this is sequences in series. And let's just remind ourselves, what sort of sequence is this? Well, 6 minus 4 is 2, and 9 minus 6 is 3. So it's not arithmetic. 6 divided by 4 is 1.5, and 9 divided by 6 is 1.5. This is a geometric sequence, all right? And we know that r is 1.5. Remember, r is any term divided by the term before it. So r is 1, 5. Now the question asks, which will be the first term to exceed 20 million, to be bigger than 20 million? What we're going to do, we are going to find out which term is equal to 20 million. So remember a, r to the n minus 1. Now we don't know what n minus 1 is. Okay, there's an equation. How many variables in that equation? Just one, Ellie Lord one. All right, we're going to divide both sides by 4, and so we're going to get 5 million. And now we've got 1.5 to the n minus 1. Now, that's in Kinga. Our variable is in the exponent. So what we're going to do, we're going to write this into log form. So n minus 1 is actually the power that we need to put onto 1.5 to get 5 million. And let's see what that is. So let's take a look. Log base 1.5 of 5 million. And what we get is about 38.04. Now remember, that's not n, that's n minus 1. So n is actually going to be 39.04. N equals 39.04. Now, is it possible to have a 39.04 term? No. So which term will be the first to exceed? Remember, these terms are getting bigger and bigger. So the answer is T40, the 40th term. Okay, and we're going to just quickly show you kind of how this looks. Okay, so what we've got here, we've got a little simulation and an Excel spreadsheet. A is 1, R is 2, those are the terms, but remember we had 4 as our first term, and then 1.5 as our, 1.5 as our second, as our common ratio. So notice there are our terms, 4, 6, 9, and this is the term number. Right, now if we scroll down here, we will see in fact that the 39th term is just a little bit less than 20 million. The 40th term is much bigger, all right, but the 40th is the first one to exceed 20 million. Okay, we could not have answered that question without the ability to find logs. Okay. Right, here's a financial maths question, and we know that it's been a while since you've seen that, but let's just have a look. I invest 100 Rand at 10% per annum compounded monthly, right? You may or may not remember this formula. This formula tells us the balance after n payment intervals, n compounding intervals with that interest rate. So we invest 100 Rand, that's P, right? And the question is asking us, how long will it take to get to 221 Rand and 82? And our interest rate is 1 plus, now it's 10% per annum, but it's going to be compounded monthly, so I need to divide by 12, all right? And then n is going to be our number of months. Okay, so that's going to be the number of months. But pause the video quickly and see if you can solve that equation. And the hint is that the unknown is in the variable, and whenever we've got the unknown variable is in the exponent, and whenever we've got that, we can use logs. So pause the video quickly, have a go and see. Right, let's first divide both sides by 100. Okay, and when we do that, we're going to get 2,2182. Right, we've just moved the decimal place. 2 to the left. This is 1 plus 0,1 over 12 to the power of n. Now let's write this in log form. N is the power that we must put onto this base of 1 plus 0,1 over 12, and we want to get 2,2182. Okay, let's bring up our calculator and see how that looks. Right, so here we go. Log 1 plus, we can use our fraction button, or we could write 0,1 divided by 12, 0,1 over 12, and here we've got 2,2182, 2,2182, and we get 96 months. N is 96 months. Right, 96, if we divide that by 12 to get into years, is actually exactly 8 years. Right, so the log function is allowing us to now solve equations where the variable is in the exponent. Okay, we're going to dive back into our study of inverses, right? Suppose we've got the function f of x equals 2 to the x. What's the inverse function, right? And let's just remind ourselves, what do? The first thing we do is we write down y equals 2 to the x. Then we swap x and y around. And that makes perfect sense because we want what were inputs to become outputs and what were outputs to become inputs. Okay? Now we get y on its own. And this is where we've got to use log. Y equals log base 2 of x. And in fact, finally, we're going to write down the inverse function is log base 2 of x. Okay, there it is. I love to check. Right? I love to check because it gives me kind of a warm, fuzzy feeling inside. If we put 3 into our original function, 2 to the 3 is 8. Now let's check. If we put 8 into the inverse, what we're doing is we're saying log base 2 of 8. And that is asking what power must we put onto 2 to get 8? And the answer is 3. Okay, so this should be 8. Okay, so f of 3 is 8, f inverse of 8 is 3, we're definitely correct. Pause the video and try the next couple, okay? You can try this one and try as many as you feel comfortable with. When you're ready or if you're not sure, let the video play again and then we'll go through some. Right, let's take a look at this one. G of x equals log base 3x, right? First thing we're going to do is write it into y equals log base 3x. Next, we are going to swap x and y around. This process is the same for all inverses. And now we want to get y on its own. So what we're going to do is we're going to take it out of log form back into exponent form. Remember, the base is always the base. So in fact, y equals 3 to the x. And so in fact, if our original function was g, then our inverse function is is 3 to the x. Okay, and let's just check this out. If we put 9 into this function for x, what is log base 3 of 9? What power must I put onto 3 to get 9? The answer is 2. If I put 2 into this function, what do I get out? I get 9 out. 3 squared is 9. Notice it's changed around. Okay, if you weren't sure how to do those and you would like to now try the rest, pause the video. We're going to quickly go through them now. Right, first thing, write it as y equals 2 to the x plus 3. Next thing, swap x and y around. X is 2 to the y plus 3. Next thing, get y on its own. Right? That's going to involve logs, but before we do that, we're going to subtract 3 from both sides. So x minus 3 is 2 to the y. Now we're going to write it in log form. Right? So y is log base 2 of x minus 3. And just be careful here, we do need the brackets, all right? x minus 3. Right, we need the brackets because it's the log of that whole thing. Okay, our actual answer, and I'm going to write the answer up at the top here, is going to be f inverse is log base 2 x minus 3. And if you want to, you can check some points. If you put 1 into here, into the original function, you get 5 out. If you put 5 in here for x, you're going to get 2 in the brackets. What power must I put onto 2 to get 2? You're going to get 1 out. 1, 5 becomes 5, 1. All right, the next one, this one is a log function, and so its inverse will be an exponential function, right? First thing we write it as y equals log base 2x minus 1. The next thing we're going to do is we're going to swap x and y as we always do. Log base 2 y minus 1. Next up, we're going to get y on its own. Now, we're going to take it out of exponent form. So y minus 1 will actually equal 2 to the x. And then obviously, if we add 1 to both sides, y will equal 2 to the x plus 1. Okay, and so g inverse of x is 2 to the x plus 1. Okay, and let's take a look. If x was 5, if we put 5 into here, we get 4 inside the brackets. What power must we put onto 2 to get 4? 5 minus 1, 4, answer is 2. Let's try putting 2 into this function. 2 to the 2 is 4 plus 1 is 5. Does it make sense? It always makes sense. Okay, right, let's try the next one. Okay, we'll do the next one with an orange pen just because we can change the colors. Right, so first thing we do is we write it as y equals 5 to the x minus 2. Next thing we do is we swap x and y around. Just be careful with your handwriting that's in the exponent, okay? Now we want to get y to be the subject of the formula. We're going to take it out of log form into exponent form, and we get y minus 2 is log base 5 of x. Lastly, we're going to add 2 to both sides. So y is going to be log base 5 of x plus 2. And notice this time we do not have a bracket. We're not finding the log of x plus 2. We're finding the log of x, and then we are adding 2. Our actual answer in the correct format, in the correct notation, f inverse of x is log base 5 of x, and then add 2. Because we can, let's just check. Let's just check what would happen in here if x was 3. If x was 3, we'd get 5 to the 3 minus 2. We get 5 to the 1, we'd get 5. Let's put 5 in here. All right? What happens when you put 5 in here? What do you get out? What's log base 5 of 5? It's 1 plus 2 is 3. When you put 5 into the inverse, you get 3 out. We are definitely right. Okay. That's meant to be a smiley face. Okay, right. And the last one, okay, and again, notice that there's not a bracket here. Okay, this is y equals log base 3 of x minus 1. Swap x and y around. X is log base 3 of y minus 1. Now, we want to get y on its own. So the first thing we need to do is add 1 to both sides. X plus 1 equals log base 3 of y. And now lastly, y, all right, y will be 3 to the x plus 1. And g inverse will be 3 to the x plus 1. Okay, let's test this out. Suppose we put 9 in here. And I'm choosing 9. I'm not choosing 5 because 5 would lead to a really ugly answer in terms of what power must I put onto 3 to get 5. What power must I put onto 3 to get 9? And the answer is 2. Take away 1 is 1. Now, let's see if we switch this point around and we put 1 into the inverse, do we get 9 out? Let's check, all right? Let's put 1 into the inverse. 3 to the 1 plus 1, halal. We get 3 to the 2, and that's 9. Right. I'm hoping that this makes sense. We are finding inverse functions. What we're going to look at now is the log graphs. All right. We've done exponent graphs before, but just to show you, the inverse of 2 to the x is the log graph, log base 2x. With log graphs and exponent graphs, this is a really important idea. If the base is greater than 1, then they go uphill. And by uphill, we mean as we look at them from left to right. Both of these lines are sloping uphill. We'll talk more about that when we do calculus. But for now, I think it's fairly obvious that they're going uphill. Don't tell me, Paul, we're going downhill when we go this way. We don't go this way. Okay? We're going to go from left to right, the same way that we would read. Okay? Left to right. Okay? Right. So let's get rid of that. And let's now have a look at these two graphs. Notice that they're inverses of one another. Here, the y-intercept is 1. That point's full name is 0, 1. Swap it round, 1, 0. This point over here is 2, 4. Swap it round, 4, 2. This graph has got an asymptote, a horizontal asymptote, which is the x-axis. Its equation is y equals 0. This graph, the inverse, has got a vertical asymptote equation, x equals 0. So what was x becomes y, all right? Right through. We're going to draw some just now. If we look, and we did speak about this previously, but if we look at the domain of our blue function, remember domain is how far left and right the graph goes. X can be anything. All right, there it is. If we look at the range of our exponential function, remember range is to do with y values, how far up and down it can go. It can only go above 0. Right, now let's look at the domain of the inverse, the how far left and right the inverse can go. And that is, in fact, you'll see it only goes to the right of 0. X has got to be bigger than 0. Okay? What about the range of this red graph, the inverse? How far up and down does it go? It goes everywhere. We say that y can be any number. Y is an element of the real numbers. Okay? And what we want to reinforce with you here is that this becomes that. The domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. Okay, right. And then obviously the function's got a horizontal asymptote and the inverse has got a vertical asymptote. Okay, we're going to ask you, so we just want to quickly show you that if you've got a base that's less than 1, the base is less than 1, then the graphs go downhill, both of them, the log graph and the exponential graph, right? They both go downhill. Sorry, just struggling to get this here. The base is less than 1, they both go downhill. The exponential graph being the blue one and the log graph being the red one. Okay, what you'll notice again though is that the domain of the function becomes the range of the inverse. You can put anything into an exponential function, and for that reason you can get anything out of a log function, okay? Its corresponding log function. You can only get positive values out of the exponential function, and because the inverse is taking the input, the outputs as inputs, you can only put in positive values into the inverse. Okay, we're going to ask you, before the next lesson, we're going to ask you to try and draw this graph and its inverse on the same set of axes. Write down the domain and the range of each. We actually did very similar exercises previously, but we only did them with parabolas, straight lines, and I think we did a hyperbola as well. Now we know about log and exponent graphs. Okay, we will look forward to seeing you next time.